Good afternoon, everybody. My name is Andrzej Katunin. I'm from St. University of Technology, Poland. My group, working for years with the phenomenon of self-heating in polymeric materials and polymers, I would like to introduce firstly the idea of self-heating phenomenon, which research we performed to date, and on what we are focusing now. So, if we talk about the self-heating effect, the genesis of this effect is in viscoelasticity of polymers. Since we have out-of-phase oscillations between stress and strain amplitudes, we have some difference in phase, and it results in energy dissipation. Most of this energy is dissipated in heat, and in the case of polymers, we already saw a presentation at the beginning about heating in steels. So here, these heating phenomena are much higher in intensity. So because of polymers are generally low conductive, I mean thermal conductivity, this energy is stored into the structure and may cause some dangerous effects. In the case of cyclic loading, in the case of fatigue loading, we have some significant acceleration of degradation in the structure. So in this chart you can see some experimental results. So we have basically two scenarios experimentally achievable. One scenario is the stationary case. So after some increase, we have temperature stabilization, and the non-stationary case, which is much more dangerous. You can see that temperatures we can achieve here are really high. So in the end, we can even pass the Tg value for a given polymer, and this effect may significantly accelerate fatigue processes. So we did some studies on criticality of this self-heating effect, just to have a knowledge about at which temperature this process of degradation start accelerating. This is important in particular from the point of view of performing fatigue tests. So we need to know up to which temperature it is possible to heat up our structure to not initiate accelerated degradation. So since in non-stationary case, so in this case, we have a situation that loading parameters are almost not influencing on the process. So this critical self-heating temperature can be considered here as the material parameter. And we did a lot of tests to determine this temperature. Here you can see the typical self-heating curve, and it is divided in three fundamental phases. The first phase is the result of thermodynamics, second law of thermodynamics, so it is just the temperature increase because of that. Here, in the second phase, you can see linear increase of temperature, which is a result of mechanical degradation. So here in this phase, some microcracks start to appear, and in the end of this phase, these microcracks are consolidated in the macrocrack, and we have a very fast propagation of the defect because apart from the self-heating effect, so the viscoelastic induced heating, we have additional frictional heating here due to the friction of surfaces in the crafting. So it's of course ends with the breakdown or failure of the structure. Here you can see some results of tests. So the blue line is the self-heating temperature curve, and the simplest method we applied is the approximation, just the approximation of this curve. When these curves start not to coincide, this point of non-coincidence is our critical self-heating temperature, and the green color is the result of acoustic emission testing. So you can see it is mainly coincide, and for this material I thought it can be considered as the material property. For this material, this critical self-heating temperature is about 60 degrees. We did also some static strength tests. So we used specimens which were loaded up to obtaining some specific temperature, self-heating temperature, and then for these specimens we did some quasi-static tensile tests. As you can see, excuse me, and as you can see, this drop is also observable at the similar temperatures. Finally, we did on the specimens prepared in the same manner, we did computed tomography tests just to look inside, to check what is going on inside, how these cracks propagate and what is the damage mechanism. And these plots are reconstructed from CTs. Blue color is a crack, red color is delamination, and it started from 55 degrees of Celsius. At 60, you can observe some cracks in the material, and then it propagates from the surface to the middle plane of the structure. Then, because of this process is, as I told, is critical for fatigue loading, we started investigating what is happening when we apply cooling, and we tried to model somehow this process just phenomenologically. Here you can see the equation which describes all the process. So typical heat transfer equation where the function Q is our source function, which determine actually the self-heating. This is described by this equation, and from the thermodynamical point of view, we have such an equation. Qd here is our generated energy, and Qc is the influx of conductivity, and Qr is the heat flux of radiation. So we started to investigate the process, and from theoretical point of view, we are able to obtain three scenarios. The first scenario, when this radiation can be omitted here actually, because the process, conductivity can be omitted because the process is on the surface, so we know we have now the conductivity through the thickness, and generally this part of the equation, if it is lower than this part, then we have non-stationary case, or case 2. If it is higher, we have case 1, and if it is in equilibrium, we have case 3. From a practical point of view, it is very, very difficult to obtain case 3, to have these parts equal to each other, because any disturbance in this parameter leads to have case 1 or case 2. So you can see it also in this previous plot. What we can have here is the parameter alpha, so thermal conductivity here in this equation. This is the parameter which describes us our problem, I mean the case from this plot. And we tried to test some, we did some preliminary tests for loading, fatigue loading of composite structures that are subjected to self-heating with air cooling. Here you can see the experimental facility. So we did some measurements. I mean the measurements of temperature, of loading, controlling the loading, also acoustic emission, and you can see here the installation which allows us to blow air onto our specimen. On the chart below, you can see 3 cases we tested. So the case with no cooling, and 2 cases with cooling with different speeds of cooling. As you can see, these are the temperature evolution curves, just like I showed you before. As you can see, the difference is really huge. Where when we have air cooling of surface and when it is not cooled down, so the residual life with the exactly same loading parameters is much longer when we apply cooling, forced cooling in this case. And also the results for acoustic emission. So you can see also the same situation for acoustic emission, for crack initiation, this initiation, so the increased activity in the case of cooled down specimen loaded with the same parameter as in this first case, blue line. You can see that acoustic emission activity is much lower in these cases where we applied surface cooling. And some alternative scenarios of cooling, what we can generally do here is the forced convection, and here we can steer with our alpha, with our conductivity by increasing the speed, for example, of our blowing air. And another case when we can change the ambient temperature, which also may change the surface temperature, and in the result may cause the decreasing of intensity of degradation. Some conclusions were maybe why we are doing these tests. So first direction which we are working on is the new method of non-destructive testing, which is based on thermography. So we use self-heating effect as the excitation of thermography. There are some cases when we cannot apply some typical heat sources for thermography. We already submitted this method for patent protection 2 years ago, and we are still waiting, it is pending. And another direction is the very high fatigue tests of very high cycle fatigue tests of these materials. Generally we are working with accelerated very high cycle fatigue tests in cooperation with our partners from Freiburg, from Germany. And there is a problem because we're loading it with ultrasonic frequencies, and during this process the heat up is really significant. And this work in particular is a step for solving the problem by cooling down the specimen during this process. Using the occasion, I would like to show you one of my latest books. It is about non-destructive testing using vibration-based methods and with application of wavelengths. If somebody is interested, I have one copy here and I can share it for free. So just after this session, come and ask me for this book. Thank you for your attention.